right, here we are back here at land of room 230 AP Chem. So we've been talking about last night the intros of acid and bases, and all those funny faces. Oh, I rapped. Any case, I want to go over electrolytes and non-electrolytes. I see people had a lot of fun with that from last night, from the submissions. It's amazing how some people, the first time they get a 25, and by the last time they're 100. I'm like, oh, what's going on there? Is it their turn to take some mime hits? I don't know. Not a mime hit. I forget it. Any case, so it's important as we go through the acid-base chemistry to understand this new term called electrolytes. So in the word electrolyte, there's electricity. But there is a little bit of confusion. I get it. All right? So I added some notes this morning because I had nothing else to do besides, well, grade your quizzes, your tests, your labs, put them in Power School, figure out today's lessons. Of course, nothing else to do besides figure out the Zoom Meet logins and put in an alternative website to the website I'm building every day, as you can see. Okay, sorry. Any case, so what are electrolytes? Electrolytes, and I'm spelling it loud and proud because I wrote it so much this morning, I know how to spell it. So electrolytes, okay? No, I don't. Okay, I've got a Y. My big moment, I failed. Okay, so electrolytes. Now these guys are nothing more than a solution that can conduct electricity, okay? Or I should better yet say electrolytes, because they're not always a solution. That's not the best answer. Electrolytes are a system by which electricity is conducted, okay, because of moving charges. So for the most part, who is an electrolyte? Well, first and foremost, sodium chloride, we know, is made of positives and negatives to the millionth time. You don't need me to raise this up, but I did anyway. Okay, obviously it could be KCl. There are many more examples than NaCl. But if I have solid ionic compounds, they are not electrolytes, okay? They don't even conduct electricity because the ions don't move. So if I take a beaker, okay, all right, right there, and I place some solid sodium chloride. Again, pour like a what? Okay, like a is it a rich person? I just think it's a, I don't know, someone who pours fancy. All right, and of course you know me to be fancy. Okay, so I take my Ernie, who is nothing more than plugged in. There's a DC current going through here. All I got to do is close the circuit, and Ernie should light up. Of course, I'm using metals here because metals conduct electricity. Metals are not electrolytes. Okay, there are compounds that have free moving electrons. We'll talk about that. But when I put these two electrodes into solid sodium chloride, there is no conductivity. These ions can't move out of the crystal. Okay, so therefore they are the solid ionic compounds, no matter if it's sodium chloride, potassium chloride, sodium fluoride, whatever combination of positive negatives that are in a solid phase. And by the way, all ionic compounds are in a solid phase at room temperature or at STP because they attract each other strong enough to make this low energy arrangement called the crystal lattice. And so if I was to put a negative here, this positive can't move out of the crystal because even though you're seeing it two-dimensionally, okay, this guy is surrounded by four negatives, but there's actually a negative, okay, stay with me, there's a negative on the other side and a negative in front, okay? If we go over here for people at home, so this sodium right here, there's a negative on top, and here's my hand, okay, and I go behind it, so I've got top and bottom. So there's 6 ions keeping it there. Therefore, the ions can't move. So when you think of electrolytes, you think of the idea that there are free ions. And in order to be a free ion, you can't be in a crystal. These have ions, so it's important that you understand that ionic compounds are never electrolytes. They never conduct, okay, in the solid state. However, party people, if you were to melt them, now I know that I said solution, so I did misspeak, but if I give these tremendous amount of heat, ionic compounds, because they are positives surrounding by negatives and vice versa in very stable low energy condition, you've got to add a lot of energy to pull them apart into what we call molten sodium chloride. We've dealt with this because if I put a what? Electrodes into this molten state and make, let's say, this electrode, okay, negatively charged, it'd be a cathode, the sodium would come running, and I would force the sodium to reduce back into pure sodium. We've already done that in electrolysis. So molten or liquid sodium chloride will conduct electricity because the ions can migrate in the liquid state, but you would need a lot of heat to do that. And if you lower the temperature, they would recrystallize. So this is an electrolyte as well. So ionic compounds do conduct electricity in liquid state. That I can't do. Like that, I don't have enough heat here to melt. I need something way over 1200 degrees Celsius, and I can't do that safely in a lab here, unless I do a thermite reaction, but no, I won't do that. All right, so these do conduct because the ions are free in a liquid state. That's important, okay? All right, and of course, if I take my ionic compound and I dissolve them, hey, now I have free ions. Yes, we know the negative part of water is going to attract the positive ion, which, by the way, is bigger. Why? Sodium, when it became positive, did what? Gets bigger or smaller. In fact, it should be smaller. Don't know why. Lose an electron, you get smaller. So that should be smaller. I feel like they got these mixed up. Yeah, that should be Na plus, and that should be Cl. This should be Cl. Ooh, Christmas. All right, whatever. Don't worry about the size of the ions here. We got them messed up. The bottom line is, I gotta work on that diagram. But bottom line is the ions are free, even though they're being surrounded by the water and those molecule ion attractions, like famous boyfriend, famous girlfriend. Water can compete for those charges. These ions, even with their water surrounding them, are free to move. Okay, classic case. So I have my water, my sodium chloride. I add some Vasa or some water, and we can see Ernie light up. Why? Because now the ions are able to move through the solution. So if I was to put a negative here, okay, well, the positive ions would come running, which would make this side, the remaining side, negative, and there is how the charge is conducted. How do we conduct a charge through our neurons? Our body talks to our environment, all these messages, okay, our own body through the channel of nerve impulses. We have an action potential. So our nervous system sends signals, electrical signals. Hey, the reason why you're hearing me right now is because there's a sound wave hitting your eardrum. That eardrum is pounding on the endings of nerve fibers that is causing an action potential to occur and sending a signal to our brain to interpret that sound. Very similar to our eye. Our eye are picking up wavelengths of light at the end of nerve fibers, optic nerve, and going to our brain. These signals, I'm moving my hand because I'm telling my muscles to do so with nerve endings. We can measure this electricity. And this electricity that we send through our body is due to ions flowing in and out of our neurons. AP Bio, for those that were there last year, you learned about these gated voltage channels where we opened up the sodium and they came rushing in, and the action potential rushed through. The movement of ions. When our body doesn't have enough of these electrolytes, we don't survive. We have to have enough of these ions in our body for our nervous system to work. If our nervous system stops, okay, so does our heart, digestive system, okay? Our nervous system is an autonomic nervous system that runs without us thinking. Automatically keeps our heart beating without us thinking about it. Got to keep thinking about beating my heart. Doesn't work that way. Or I forgot to breathe last night. Didn't make it. Doesn't work that way. Okay. So this is really important. Okay. In fact, I don't know if I told this story in AP Bio, but when we think about electrolytes, we think about dissolved ions. They're really important. They help electrical charge, especially in the nervous system. But there was an important, well, a really sad radio accident where someone was trying to win tickets to a Britney Spears concert. This was way back about 10 years ago, I think. And the radio host said, hey, to win the contest, see who can drink the most water in an amount of time. Well, this mother of, I think, 2 or 3 daughters, doesn't really matter, drank like 10 gallons in a short period of time. Of course, she had to go to the bathroom, okay, and basically going to the bathroom that much for 10 gallons of water took a lot of these ions out of her system, and she didn't have enough dissolved ions to conduct electricity in her nervous system, and she died. She died, okay? Those guys got fired. I don't know if there's a civil lawsuit or not, but we need to have them. In fact, years ago, when football players would go in August, okay, and work out and put the pads on and hit, they knew that they're sweating out a lot of their what? Salts. They used to give them salt pills Now, they were not very smart about it. They would overdo it with salt pills, and if you know about hypertonic and hypotonic, they were actually making them more dehydrated. But the idea was they were sweating so much and drinking so much, they could die by losing iron, so they were giving them salt pills. Today, of course, you don't need so much of that salt. Today, if you look at a Gatorade bottle, it'll say electrolytes on it because they just add some sodium chloride, a little bit salty, because if you sweat a lot, you do want to replenish your electrolytes. All right, so these are things that are around you. So when we really think of electrolytes, we think about dissolved ions. What if it doesn't dissolve? What if I got something like calcium carbonate, which is a salt, but the positive 2 and the negative 2, they're not free. So things that are not soluble are not electrolytes. They have to be able to be free. So when you think of electrolytes, it's mostly dissolved ions. Yes, liquefied. This state is pretty rare though. Okay, in nature we just don't have a state where I can melt sodium chloride. Okay, it's 13, 14, 15, 16, 17, 1800 degrees Celsius to melt these guys because they're stuck together so strongly coulomically. This is where we live in terms of biology and most of the time. So electrolytes are really about dissolved ions, although we can talk about NaCl. So ionic compounds never dissolve in a solid, but in a liquid state or aqueous state, okay, absolutely, because the ions are free to move. Okay, now I introduced some other things that we talked about. We don't only just have ionic compounds, we have molecules. Molecules have an exact number of chemicals. And the reasoning behind that is because they bond differently than positives and negatives. They bond with their outermost electrons. Okay, when I think about it, okay, a molecule has a definite number of atoms based upon electron arrangement. And it's based upon stability. For instance, here's oxygen, and here's hydrogen. Oxygen has 6 valence. Now we've done this over the summer. You may have done it last year. We'll get to this, but I want you to get this feeling. So oxygen has 6 valence electrons. It starts out here, okay, and it's 2 away from being stable. It wants to fill. It wants to have that 8. We'll talk more about that. So what I'm going to do is show the dots. And the reason why we show the dots as electrons is because we know that oxygen is not strong enough to pull electrons away from other non-metals. Non-metals are the small atoms that love to attract their own electrons, and they fantasize about gaining more. Hope you ain't too uncomfortable with that. Okay? So the point I'm trying to make here is that these guys are fighting for electrons. So they're pulling on them. Okay? So they're not going to be able to pull. Hey, listen, sodium is a metal. Electrons way out here. Chlorine's attracting to it's got to pull that one. This becomes negative and positive. That's oxidation reduction. That's how that happens. These guys can't occur that way because they're both strong. Think of a tug of war of 2 strong people. All right, I'll give you this analogy. Okay, here's sodium, a metal, big atom, loosely held electron. Here's chlorine, a non-metal with 7 electrons in the outermost. We'll get to that. Weak attractive forces for the outermost electron. That's why it's a big atom. What? Strong attractive forces for electrons. That's why it's a small atom. Okay, if they were to have a tug of war, it would be like this. And I do this with my youngest, although he's getting bigger. Okay? Before I leave for work every day, and it's early, so I wake him up, push him out of bed. Let's get up, let's go. Time to see if you're a man today. And I do this. Okay? And I get him up. He's wiping his eyes, he's crying a little bit. Stop it! Time to be a man today. So we step up, we go in the kitchen. We have the most room in the kitchen. And I have a rope that just sits there. He knows what to do. He grabs the rope. And we have a tug of war. And it's mano, old man, old man and a kid. Okay? And I grab that rope. I say, you ready? Set. Sometimes I go before he's ready because I want to show him that he always has to be ready. And I say, go! And I pull as hard as I can. I do not give him anything. If he's going to earn something in life, he's going to really earn it. He tries, and I pull. And he goes forward, and I rip the rope right out of his hands. He flies down and falls most mornings, head first, sometimes crying. And I stand over him with the rope, because I am victorious, look at him and say, who is your daddy? Okay? The point of that demo, okay, he didn't win this morning either. But, no, I don't do that. I give him gloves, okay? All right.
On video, so.
What's that?
We got that all on video, so.
Well, yeah, listen, he'll get over it, okay? In the afternoons, Monday through Friday, we're in therapy. Okay, but the point is, okay, one day he'll beat me. All right, Sean, one day I'm going to be mad about that. I don't want to do it, Sean. All right, now, the point is, that is exactly what happens here. That's me. This is my son, and I yank the rope away. And now this is negative, positive. We stick together by differences in charges. But if we're talking about small atoms who are both strong, let's say me and my evil twin Mongo. You didn't know I had an evil twin Mongo, okay? We're twins, so we're about the same strength. Now, Mongo is a little stronger because if you were named Mongo, you'd work out too. Okay, now. Listen, all right. Ben, I didn't have to. Nice name, Mongo. Whoa, he's a little weird. Oh, but he's muscular. Okay, now. So, me and Mongo, Kim's over for Thanksgiving, and we always have a tug of war in our house. It's kind of a weird thing. So, he pulls, okay? And we're about the same strength. He's a little stronger, but we're not strong enough to pull the rope out of each other's hands. We're forced to share. And that's what happens here. So hydrogen brings one valence electron, and looky here. By sharing, hydrogen feels like it has what? 2 electrons that fill its energy level. And by sharing, this oxygen feels like it has 8. And by sharing, this one feels like it has 8. And this is how it works. They fill their energy shells. There's something about filling their energy shells. They can't yank the electrons away. So what we do here is show that they are covalencing. Okay, they're sharing. And it looks like this. A pair of electrons is a bond. I call this the eyeglass method. And a lone pair. And that's hydrogen peroxide. And that's a molecular formula. That's exactly the number of atoms that makes this particle, H2O2, a molecule. It's made of nonmetals. And that's the molecular form. What would be its empirical lowest ratio? Oh, yeah. All right. So, any case. So, when we get to, hey, carbon, oxygen, hydrogen, the small guys, they are going to fight for electrons. If you got that, they fight for electrons. That means that they're what? Pulling on these electrons. Therefore, if they're pulling on electrons, even though we have a lot of them, every one of these pairs of electrons are being pulled on by the other, by me and my evil twin Mongo. Are these electrons free to move if both atoms are pulling on them? No. So sucrose, okay, another what? Woo. Okay, is a molecular compound. Why is it molecular? It's made of covalent bonds. And it's covalent bonds because it's made of the small guys, the nonmetals above the staircase. They're fighting to share. And because they're all fighting for these electrons are not free to move. What conducts electricity? Free moving charges. For electrolytes, it's definitely the ions. So this is not made up of ions. But it has electrons all over the place, but they're not free to migrate. So solid molecular compounds or liquefied molecular compounds never conduct. Sugar, sucrose, which is a disaccharide, glucose and fructose, doesn't matter, don't conduct. Pure water does not conduct electricity. Why? It's made of hydrogen and oxygen. It's a molecule. We call it a molecular compound. It's important you know the difference. Electrons are being fought. Okay, yes?
But aren't there like H plus and O, or is that just like not enough?
Not enough. And we'll talk about that. I'm going to add to that story. But you're right. There is some naturally occurring H plus and OH minus, but the concentration that exists in equilibrium is so small, not enough. That's a great point there. And I was going to add to that story later, but thank you. All right, so this doesn't conduct. Now, if I add water to it, okay, spring water, crystal geyser. I love the names of things. Crystal geyser. Whoa, okay. Meanwhile, some guy in Deer Park was taking his, the hose, spilling it up into the garden hose. They had crystal geyser, yeah, right. All right. Made in Deer Park. Made in Riverhead. I didn't see the geyser. Okay. It's over there. It's easy to miss. It's by the pumpkin patch.
They have their hose.
It's by the green screen. So I, of course, make sugar water, and Ernie doesn't light up. It doesn't conduct. If I was to melt it, it wouldn't conduct. Non-electrolyte, it doesn't melt as a solid. Okay, now, last compound, never considered to be an electrolyte. Metallic substances like copper, bonded to copper, bonded to copper, bonded to copper. We never say that. If I've got iron, bonded to iron, bonded to iron, it's just a bunch of iron nuclei. These are the nuclei. Inside of an atom, there's protons and neutrons, but the inside of the atom is positive. Electrons are loosely held with metals. So loosely held when we have a crystal of metals, the electrons are free to stay within the crystal. They're attracted they're attracted weak enough that they can move throughout the crystal because they're still attracted to someone else's positive nucleus, but not so weak they just can leave. So we say that metallic substances, when they're in a crystal pattern, are basically in a sea of mobile electrons. I put a negative here, all these negatives will repel and go to this side of the crystal, and you just made the compound conduct electricity, okay? It's not an electrolyte because we're not in solution, we can't dissolve a metal. So when you think about electrolytes, here are what we have. Ionic compounds that are melted or molten, very low rare occurrence, because you don't see that naturally. Here's the biggest one, ionic compounds that are dissolved, free ions, okay? But we also have base solutions because we know that, hey, bases produce hydroxide ions in enough quantity, they light up Ernie as well. And acid solutions, okay? Same thing. They give off H pluses. So free ions are really what the electrolyte. What's not electrolyte is molecular compounds. Metallic compounds do conduct electricity in the solid phase or liquid phase, but they are not considered to be electrolytes in terms of the ions. So I hope that clears up anything you might have had. Okay, so let's go on to, all right. Okay, let's turn this off before I shock myself. All right, let's go to the acid-base guy's worksheet. All right, let me just unplug him. Okay, Ernie's so cute. He's been with me for a long time. All right, so let's go to that worksheet, and we got some more demos coming up. All right, pen of apple. All right, and I've got to share my screen. Just stay with me. Where would you go, right? Okay, so we go, screen mirroring, Brodsky. And let's do this. So now we're going to talk about the actual definitions of acid and bases. I've given you some basics of the acid base. Sorry, but the pun's going to continue on, so sorry about that. But it'll be all white. Okay, so moving on. Ow, I stepped on something. I don't know why I said ow. It's the other thing that would say ow. Okay, I need a cursor. Sorry for the cursoring. Come on, Morgan, you need to laugh this morning. Is Morgan D out there? Put the donut down, Morgan D. Okay? All right, here we go. So hopefully you guys at home have typed this. If not, just follow along with me. Okay? All right. So, interesting enough, and I say that because, start. Excuse me? Oh, I thought that was What's going on here?
Christina said funny.
She's mentioning planets,
Yeah.
but referencing the end of the.
She only does the suffix of the year.
Yeah. Okay. What's going on here?
The last part of
Okay, I got
Wait,
this.
guys, what do you put for your favorite element?
My favorite element?
I put the tastiest one. I put arsenic.
Oh, rat poison. The one I pick is the one that sounds the coolest. Molybdenum.
What the?
M.O. yo! I'm sorry. Okay, it's a Riverhead thing, sorry. We just scream when people, when we feel important, we just scream, what's up? Okay.
Xenon has an X in it.
Okay, hey, listen, we all have our ways. Okay, so table K. K? K.
Me.
K?
Yeah.
K.
Okay.
Oh,
Wait.
K, not OK. Thor, come on. Tor. It's a Thor. It's Tor. Right? There's no H? I want to say Thor, but it's Tor.
It's
It's Tor. All right.
short.
I like it. All right, so common acids. So they give you this, and you have this in your reference table. So what do we know, party people, is that if you've got a common acid on a Regents test, and I'm leaving you have this, what is important is they put something in front to scream to you that this something loves to be given off. Can you guess what is loving to be given off here? The H, but it's more than just the H. It's an H plus, which we call either a hydrogen ion, but if you're cool, okay, we say proton. Because an H plus is a proton. All right, so that is screaming to you. So, we have some acid-base definitions we have to know. Arrhenius, he's not from Uranus, okay? So I'm not sure what we're talking about here today, but Arrhenius, sometimes I think the H is silent there, okay? Which I don't even know why you need to have it if it's silent. All right, but hey, let's make the English language tougher than we have to. All right, so it's like having there's an actually Y at the end of this that's silent. Could there be a whole like word after that? Like, where's your essay? I wrote it, it's just silent, okay? That's the same understanding as why that is silent, I think. I don't know. No, back when it was first, I'll forget it. Okay, so Arrhenius acids. Okay, this is the most simplistic definition. As we talk about AP Bio all the time, we go from simple organisms to more complex. It's called Occam's razor, right? It's the logical way that we think things. Things don't become more complex and go backwards. So obviously the first definition of acid and bases was the most simplistic. So up here, we're going to write Arrhenius. All right, A, R, R. H is silent, but I have to write it anyway. I feel like it's ridiculous. So there's my Arrhenius definition. Okay, and I'm going to write that there. And that's going to remind me that that is the smallest scope definition. So he was the first to define acid and bases. So the Arrhenius acid would be an acid, all right, that produces H pluses in solution. In fact, they would say the only positive ion in solution is the H plus. So it produces H pluses in solutions. So if you're in an acidic solution, you produce H pluses. So if you're considered to be an Arrhenius acid, hey, you must have H pluses that can dissociate the molecule. And clearly, we can see from table K, that, hey, they have an H in front that can dissociate. So these are all examples of Arrhenius acids, okay? Are there acids in there we're going to see today that aren't Arrhenius? Yes, because that was the most simplest definition. Can anyone guess what the base definition was? This is the most simplest definition. To be a base, yes, you produce OH minus in solution. In fact, the only negative ion is the hydroxide. Very simple. Hey, you're a base, you produce an OH minus. If you're an acid, you produce an H plus. This is the simplest. There's better definitions. If we look, table L, let's take an L right here. Right, Christina? All right, now, we look at table L, we can see, oh, here are salts. Sodium plus, K plus, calcium plus with an OH minus. We can clearly see that these guys right here are Arrhenius, H is silent because we have to be difficult, bases. Why? Because they clearly have an OH minus in the salt. What are bases? They're nothing more than soluble salts with that polyatomic ion hydroxide. Okay. And of course, as an example, these guys here are Arrhenius acids because they have an H plus. All right, as I said, that is the most simplistic definition. It doesn't work all the time. And so we have figured out that there are going to be some compounds that we know that when we add to water will make the pH drop, be more acidic, or make the pH go up and be more basic. So we've seen things that can act as bases, okay, or acids that don't follow this definition. So we need a new color, okay? And so we need a more broader definition that encompasses Arrhenius, and that would be the Bronsted-Lowry definition. Bronsted, Lowry, two guys. Bronsted, Lowry.
That like French letters.
Not really sure.
It's a good question.
Okay, not sure. But here's what I do know. Here is a Bronson-Lowry base, NH3. We know ammonia is basic. People use ammonia as cleaning agents all the time. In fact, the #1 active ingredient in Windex, okay, or cleaners is ammonia. Why? It's a base, which means what? It can break up things like fats because as a small negative ion, it can push electrons out of, okay, bonds. Okay, as you saw last night, that one little crazy mechanism was a base. You pushed electrons out, okay? So, what is its definition that includes their Arrhenius definition, but now expands to cover some other chemicals that don't fall under that, okay? And so, it's very simple, but a little more complex. To be a Bronson-Lowry acid isn't about just producing H pluses. We know H pluses are highly reactive. They don't hang out in solution, so Arrhenius definition is definitely limited. The H pluses are going to go somewhere. They're going to go somewhere where there is some negatives. They're a heat-sinking missile. So the best definition here is, do you want to add to that?
No.
Okay. All right, so to be an acid, you are a proton donor. So this doesn't mean you just produce H pluses. This means that you what? You donate protons. I like to think of this a lot like redox. Redox, the one that oxidizes, donates electrons. Well, the acid gives its H plus to something. And what do you think the base is? If the acid is donating the proton, what does the base do? Accepts it. Okay, if you guys said that. So it's a proton acceptor, which means it accepts protons. Now, we know that H plus is a heat-sinking missile for electrons because it's so small and positive, it's going to go find some what? It's going to go find some negatives. Okay, that means a base has to have some negatives that's attracted to. So, I just showed you in table L, take the L, okay, that these guys are Arrhenius bases because they produce the hydroxide. We know aqueous ammonia is very basic, okay? When we look at the structure, it doesn't have a hydroxide. So how can it be basic? Well, let's see. And this is important. Okay, let's look at this. Okay? So here's my ammonia. Now, I'm going to do a Lewis dot diagram like I did here for ammonia so you can understand it better. Okay? And we'll do it in blue or purple. I have no idea what color this is. So here's my ammonia. I'm going to put it right here. Here's N. Okay, does anyone know how many valence electrons does ammonia have? I mean, N have. N is right here. So that would be 1, 2, 3, 4, 5. 6, 7, 8. It wants to have 8, but it has 5. Okay? For those that didn't see what I was pointing to, just think it has 5 outermost electrons. We'll get there. I'll definitely teach it. So I'm going to go 1, 2, 3, 4, and 5. What's so special about ammonia or nitrogen-based compounds, sorry for the pun again, is that they're the bases in our bodies. DNA is deoxyribonucleic acid. And we learned about nitrogenous bases, base pairing in our DNA. And if you remember, your nitrogenous bases had nitrogen. They're a reason why they're called bases because they have this lone pair. What's that lone pair good at? Providing negatives, yes, for that H plus. So stay with me for a second. Let's finish this out. We have hydrogen. It has one valence electron. And you can see why the structure is NH3. Because nitrogen has 1, 2, 3, 4, 5 valence electrons. Hydrogen brings one to the table, and it's me and evil twin Mongo having a what? Tug of war. These are 3 bonds. But there is a lone pair, and that's the most important thing about this. There's a lone pair sitting out here that's negative, okay? So I'm just going to draw that here, and I can do that. Anytime nitrogen is bonded to 3 things, it's got a lone pair. I'm going to draw that right there. Okay, and here we have water. So we're going to drop ammonia in water, and that's what you do. You don't ever have pure ammonia. If you did, you would not survive cleaning. You would just pass out, okay? It's too noxious. So you do dissolve in water. Here's what happens. Go back to being blue. Water donates an H plus here. It gives up a proton. Now, a proton has how many electrons? 0. And how many electrons does hydrogen need to be happy and stable? 2. There's a pair sitting right there. There's an electron-rich area to accept that proton. And what does it become? In the future. Future. I talk like this when I'm 80 and still teaching. All right, let me get to the board, okay? So this gains an H plus, all right? So it was NH3, so what's it now? NH4, but wait a minute. It gained a proton. Did it gain electrons? This is neutral, isn't it? I'm adding an H plus without any electrons. Can you guess what charge this is? +1. And party people, if you go to table E, this is the ammonium ion. Ooh, okay. What does OH do? If water just lost H's, okay? Think about water for a second. Water looks like this. 1, 2, 3, 4, 5, 6. Here comes the H. There's its electron. It feels like it has 8. If it loses an H, it loses a positive. Isn't this -1? Isn't that a hydroxide? So it's an OH minus. And it's kind of cool when you start thinking about it, or you can pretend it is. Ammonia is a base because it accepts a proton. But really, when you think about it, what's it really produce at the end of the day? It's producing hydroxides indirectly.
So the hydrogen goes over because there's 2 free electrons that aren't really.
Right.
But then there's 4 on the oxygen when there's the water, right? So why
There
would-
are 4, yeah, so water can actually act as an acid or a base.
Oh,
That's called amphotericism.
right.
So water can do both. We're going to see both of them today. You're right. It has 2 lone pairs.
Yeah.
To be a base, you have to have a lone pair. But the idea here is when we turn about water think about water. I keep saying it in AP Bio. I'll keep saying it here. Water produces this scenario. Electron deficient H's, doesn't it? So these guys are, because this is my evil twin Mongo, who's even more stronger than I am, is pulling the rope this way. These guys have kind of lost their electrons. So they're kind of positive. So they're going to be really attracted to the negative of the ammonia, and they're able to do that. So the key here is that ammonia is a Bronson-Lowry base because it accepts protons, but when you think about it, it really produces hydroxides indirectly. What's going to make a solution basic is eventually more hydroxides are made in the solution. And this gets it done by accepting protons. If something's getting more acidic, somehow we're increasing the H pluses. Okay? Now let's talk about what this is. Because it's accepting a proton, we call it a Bronson-Lowry base. Because water is the one donating. The idea that acids have H pluses hanging out is silly. you're going to donate it. That's the acid. Okay, now party people, what is this now? Well, I need to put a double arrow here, because when you have weak acid and bases, and these guys are, you're going to have equilibrium. So the question is, well, what are these guys? Well, if we go in reverse, how does OH minus become H2O in reverse? In reverse, this now becomes the future. So in the future, it has one more H. How'd that happen? Like you just said, James.
Going back.
It accepted. It's got 3 lone pairs here, and it's -1. So this is more basic than this is, but it's going to grab an H+. So in the reverse, this is accepting. Remember, there's what? 3 lone pairs here. So this is going to be the base, and this is the acid in reverse. Now, my friends in chemistry, we have a new word today called conjugate. 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 Conjugate this. Conjugate. Conjugate. Conjugate means the same chemical plus or minus 1. So, they could ask you, and I will, and other people will, what are the conjugate pairs? Conjugate pairs. Conjugate pairs will always be acid-base, what? Forms of the same element. Oh, I'm sorry, of the same chemical. Acid-base forms. So, this is the base form of NH3. What's its acid form? Right, that is one conjugate pair. What would be the other conjugate pair? H2O and OH minus. Conjugate means same chemical plus or minus 1 H. It's a pair, okay? These cannot be conjugate pairs because they're different chemicals. Conjugate means same chemical plus or minus. Now think with me for a second. If I have hydrochloric acid, all right, let's get rid of this guy. If I have hydrochloric acid, that is my conjugate acid, correct? When it gives off a proton to something, what remains is its conjugate what? Conjugate base. Conjugate acid. Conjugate base. Conjugate acid always has one more H than its base form, because with the H you can deliver it. Look, the conjugate acid has one more H than its what? Base form. Or the conjugate base form has one less H. Okay, let me give you this scenario. If I give you the bicarb ion, HCO3 negative, ooh, I want the conjugate base of this. Is it going to have one more H or one less H? One less H. So the conjugate base of this would be CO3. It lost a positive. -2. If I want the conjugate acid of this, that would be it, correct? Check this out. Well, what's the conjugate acid of this guy? H2 CO3. This is called amphoteric. It can do what? Act as an acid, give up an H+, or accept an H. Okay, it's called a buffer in our blood. We have this in our blood accepting what? Extra H pluses, or it can do what? Give off an H+ to keep our pH. We'll talk about that. So let's talk about water. You just mentioned water. You just mentioned water. Hey, water. What is the conjugate Think about this for a second. What is the conjugate base of water? OH minus. Right? Because what? If it's a conjugate base and this is the acid to get here, you've got to lose and donate an H plus to something. You with me? Good. What is the conjugate base? What's the conjugate? What's the conjugate acid of this guy?
H3 or?
Yes. Doesn't water, just like James said, have a lone pair? So couldn't it accept a proton?
It's also accept another proton.
Hold on. So this becomes H3O plus. So the conjugate, okay, acid of water is H3O plus. Now you may say, well, Mr. Grodsky, if I donate a pair to this H, I still got a lone pair and I should be able to make H4O plus, but it never occurs. This is why I love chemistry. Why don't you think, once I have an H here, this whole thing is +1 because we added a proton, right? I got a lone pair. Why don't you think, why can't it accept another proton? Right! This thing is positive, so another positive is going to be what? Repelled by it. It's so beautiful. We don't find H what? 4 O
4 plus 2.
2 + 2 in nature. It's so weird I can't even say it. Okay? So water can act as an acid or base. Okay? Let's do this. Here is phosphoric acid, H3PO4. Okay, what is its conjugate base? H. This is the acid. The base is always going to have one less than the acid, right? So H2PO4, and you lost an H plus, so what's its charge? -1. And what is the conjugate acid of this? Yeah. Okay. How about this? If I give you phosphate, PO4, -3, you have that in your reference. What is the conjugate acid of that? That would be, if I'm looking for the conjugate acid, this must be the what? And the base always has one less, the acid has one more. So this would be HPO4 -2. Cool. All right? So, looking here. This is a skill today. And I'm going to stop real soon. I'm sorry. It's the last little piece and I'll stop today. Okay? Given this should be a double arrow. I feel bad. Guess what? I'm over it. Yep. Double arrow. Okay. Let's figure out who the acid and bases are on both sides and the conjugate acid-base pairs. Okay. So party people, how do I do this? Well, I have H2PO4 -1. What does it become on the other side? Well, it's HPO4 -2. This is HCO. You can't change. So right here is the two compounds. Right here are your conjugate acid-base pairs. Now, for me, become H2PO4 negative, become HPO4 -2. What had to happen for me to do that? Tor?
Have to give the-
Right, we had to give up an H plus. So this gave up or donated a proton. Okay? And it's acting as a what? You donate protons based on Bronson Lowry, you're what? An acid. Who's accepted? Well, HCO3 -1. So that's your base. How do I know it's the base? Because in the future, it has one more H. Going this way, it must have, which means it had to have a lone pair, okay, for it to do that. It did, and we'll see that when we do Lewis dot diagrams in the unit, okay? Okay, but here's something cool. Once you found this, it's easy. If this is acid form, other side must be its conjugate what? Base. So here's acid. Here must be its base. And if this is the what? Its conjugate base form, other side has to be the conjugate acid. And you're done. But if you don't trust yourself, go in the reverse. For H2CO3 to become here, hey, I have one less H. That means that one had to act as an acid to donate the proton. And of course, for this to be a base going forward, okay, it must be accepting one. There should be one more going that way. It's pretty logical. Who are your conjugate acid-base pairs? Okay, here's one conjugate acid-base pair, and here is the other conjugate acid-base pair. Same chemical, plus or minus an H. We're always talking about the exchange of one H. You see, Mr. Grodsky, let's got two of them, but we're only doing one at a time, and I'll tell you why. There's an ability we're going to learn tomorrow. There's an ability of how we measure how well this gives off. Think about this. This is neutral, right? Isn't it easy for a positive to leave something neutral? Now, once I give this off and becomes HCO3 negative, don't you think it's going to be harder for this to leave something negative? So it doesn't do it as well. So so we always consider the one H plus being accepted at a time and losing at a time. We don't get confuddled by, hey, it just gives off two. It can give off two. The first one's easier, the second one's harder, and that gives us actually a Ka of 1 and a Ka of 2. There's a acid dissociation constant for the first H, which will be pretty high, but then it's going to get lowered as this is negative. It's logical. And you start loving chemistry when you start seeing why. I can give you this in the rules, but seeing it why. Now, there's one more thing about Bronson-Lowry acid bases, and I'll be done today. What pops up in Bronson-Lowry definition is what happens to water. Okay? For instance, I'll show you this one. Okay? If I have hydrochloric acid, I'm not loving that color. Here we go. So I have hydrochloric acid, and I add it to water. What do I produce? Okay, well, Mr. Grodsky, I saw that water can be an acid, and I know that this is an acid, so who acid and base? Who's the stronger acid is the one who does the protonating. So if I have a list of Kas, water Ka is 1 times 10 to the negative 14, showing how much it gives off in H+. The K for HCl is almost infinity. What's Ka mean? Products over reactants, right? So this is the stronger the acid is the one that does the protonating. And I can look at a table somewhere for that. So I know that hydrochloric acid is going to donate. It completely dissociates. So it's going to force water and H+. And this is what we have, H3O+. And then we just talked about this. You don't have H4O plus 2 because the plus blocks it, okay? And of course, what's left over is Cl negative. Now, I am not going to draw a double arrow here. If this is a strong acid, this is a completion reaction. This is going to keep going until I run out. And something new, okay? We have some players in acid and base, okay? I don't know if you recognize a player, you stay away from a player. If I had a daughter, I'd say stay away from the players, okay? But, all right, we have the what? The proton. That guy's a player. Stay away from the proton. We have the hydroxide, another player. But we have another player here. This, my friends, is called a hydronium ion. I'm sorry, hydronium ion. And in Bronson-Lowry definition, from this point forward, oh, my little thing went. This is synonymous with H+. So we think of H pluses for acids, but that's not real because H pluses are like heat-seeking missiles. They're not going to stay and hang out in a solution. We're really reactive, but we're going to stay in here so you can understand me. No, they're going to go to where the electrons are. If you have an aqueous solution, guess who has the most available pairs of electrons? If you have a water molecule, if you're an aqueous solution, water's got the most available pairs of electrons. So think of this as water holding on to a proton. Think of this as a strong acid as well. H3O plus is as strong as HCl. So when you think of acids, yeah, you think of H plus as being donated, but H3O plus is synonymous with H plus. So when we think of acidity, an acidic solution, we'll stop here. If I'm acidic, I have a large number of H pluses, but really I have what? H3O pluses. Basic. No matter how I get there, directly or indirectly, I do get hydroxides. Okay. So work of home, real simple. Okay. All I want for you guys to do for homework, there's a conjugate acid-base pair sheet, and there's only 3 of them. I want you to figure out who the acid-base pairs are. Okay. And backside, you're going to omit. In fact, you're going to omit all 5 sides except for the top side. Okay. Yeah, I'm cutting out all the 5 sides of the rectangle. Imagine handing out a rectangle. Like, homework tonight. I'm passing it out. Is a cube of homework. There's 6. All right. All right. Really? Okay. So, all right. I'll do that side. All right. No, the homework's not yet. Not yet. Darn it. All right. Sorry. I got issues. You know about that. So yeah, you're gonna stop, do your homework, take a break. You should be done with your homework tonight. Oh no, you have a little bit more to go tonight by the stuff you're gonna watch. So no worries. Bye bye.